Welcome to The Explainer. I am absolutely thrilled to have you here today because we're going to decode something truly fascinating, the physics of lenses and exactly how they manipulate light. If you've ever wondered how the optics all around you actually function, you are in the perfect place. Okay, let's dive into this.
Think about it for a second. How is it that a basic, transparent piece of curved glass can completely correct our vision, capture incredibly intricate photos, or, even peer millions of light years into deep space? It kind of feels like magic, right? But it's actually just absolutely elegant physics at work.
Here's our roadmap for today's explainer. First, we'll meet the lenses. Second, the anatomy of a lens. Third, the rules of ray tracing. Fourth, forming the image. And finally, number 5, the math behind the magic. Let's get right into it.
Section 1. Meet the lenses. Converging versus diverging. So in the world of spherical lenses, we really have two main characters, and they behave in completely opposite ways. Just take a look at their distinct physical shapes. The convex lens bulges out, right? It's thick in the middle and thin at the periphery. The concave lens is the exact opposite. It's super thin in the middle and thick at the edges. Because of this shape, a convex lens brings light rays together, making it a converging lens. The concave lens, on the other hand, spreads light out, which makes it a diverging lens.
To really grasp why they do that, you can actually picture any lens as a set of stacked prisms, with a rectangular slab right in the very center. Now, when light hits a prism, it always bends towards the base. So for a convex lens, those outer prisms have their bases pointing inward toward the center, which literally forces the light rays to converge. But for a concave lens, the bases are pointing outward, which forces the light rays to diverge or spread totally apart.
Moving on to Section 2, Anatomy of a Lens, the vocabulary of optics.
Okay, to really understand how light interacts with these lenses, we need to nail down the proper terms. First up, check out the very center of the lenses. That point is called the optical center, usually marked with an O. And what's special about this point? Well, any light ray directed straight through this optical center passes through the lens completely undeviated, no bending whatsoever. And running straight through that center horizontally is the principal axis, an imaginary line joining the centers of curvature of the two spherical surfaces that actually make up the lens.
Now we arrive at a genuinely crucial concept, the principal foci. Because light can enter a lens from either the left or the right side, every single lens inherently has two of these focal points. They're the specific locations on the principal axis where light rays that come in parallel to the axis either literally converge or at least appear to diverge from after they pass through the glass.
What's really interesting here is how we measure that distance. The focal length is simply the distance from the optical center right out to that focal point. But notice the distinct difference between the two lenses we're looking at. The convex lens has what we call a real focus, simply because the light rays physically pass through that point on the other side. The concave lens, though, has a virtual focus. The light rays spread out, and they only appear to diverge from that point if you were to trace them backward.
Section 3. Rules of ray tracing. 3 principal rays.
All right, now that we've got the anatomy down, how do we find out exactly where an image will form? Well, you don't need to trace every single ray of light. That'd be impossible. You really only ever need to draw 2 of these 3 standard construction rays. Rule 1. A ray passing right through the optical center goes straight through without bending. Rule 2. A ray coming in parallel to the principal axis will bend to pass through the focal point. And Rule 3. A ray passing through the focal point first will bend to come out parallel to the principal axis.
Seeing these 3 steps in action totally clarifies everything. For the convex lens, you can clearly see the parallel ray bending through the focus, and that ray hitting the optical center just flying straight on through. And the exact same rules apply to the concave lens. Honestly, mastering just 2 of these lines gives us the absolute power to construct any image we want.
Section 4. Forming the image. From real to virtual.
Let's actually put this new ray tracing toolkit to the test. Let's start with an object that's incredibly far away, like at infinity. Think of the sun. Because it's so far, the light rays reach the lens perfectly parallel to each other. As our rules dictate, they all converge exactly at the second focal point on the other side of the lens. This forms a tiny, highly diminished, real and inverted image right at that focus. By the way, this is exactly how a burning glass works.
So the real takeaway here is that this image isn't static. As you move an object closer and closer to a convex lens, the real image formed on the other side actually pushes further away from the lens, and it grows larger. It starts out tiny, then it becomes the exact same size, then magnified. But watch what happens in that last scenario. If you move the object past the focal point, right up close to the lens, those light rays can no longer converge. Instead, they form a magnified, virtual, and upright image on the same side. And that right there, that's exactly how a magnifying glass works.
Now let's contrast all that complex behavior with the concave lens. The concave lens is just beautifully simple. It really doesn't matter where you place the object, at infinity or right up close in front of it, it will always, without fail, produce an image that is virtual, upright, and shrunken down. The image is just always formed between the optical center and the focus on the exact same side as the object.
Which brings us to Section 5, the math behind the magic, quantifying refraction.
We've drawn all the diagrams, but obviously physics is an exact science. Before we can calculate anything, we have to establish the ground rules, and these are known as the Cartesian sign convention. Just think of the lens's optical center as the zero-point origin on a graph. Any distance you measure in the same direction that the light is traveling is a positive number. Any distance measured going against the light is negative. It's the same for heights. Above the principal axis is positive, and below is negative.
So, applying this convention to our two lenses reveals something super important. Because a convex lens actually converges light to a real focus on the far side, its focal length is measured in the direction of the light. Therefore, the focal length of a convex lens is always positive. Conversely, a concave lens diverges light from a virtual focus on the near side. Since we're measuring backward against the light, the focal length of a concave lens is always negative.
And here is the ultimate payoff of our explainer today, the lens formula. 1 over v minus 1 over u equals 1 over f. This one incredibly elegant equation relates the image distance, which is represented by v, the object distance, represented by u, and the focal length, f. And as long as you follow those positive and negative sign rules we just went over, this equation works perfectly for both convex and concave lenses.
Right alongside the lens formula, we also have linear magnification, represented by m. This is simply the ratio of the image height to the object height, which we can easily calculate as v divided by u. The resulting number is incredibly informative. If the number is greater than 1, well, your image is magnified. If it's less than 1, it's diminished. Plus, a positive sign tells you the image is virtual and upright, while a negative sign means the image is real and upside down.
Finally, we often talk about the power of a lens, which is measured in a unit called diopters. The power is simply the reciprocal of the focal length in meters. Why? Well, think about it. A thicker lens has a lot of curvature, meaning it bends light pretty drastically. Because it bends light so sharply, the focal point is much closer to the lens, giving it a short focal length. And a shorter focal length directly translates to a higher power.
Let's wrap things up with a final thought experiment applying everything we've covered today. Knowing what you know now, can you use a convex lens to burn a piece of paper using just the light from the sun? And more importantly, considering the sun is effectively at an infinite distance, producing completely parallel light rays, exactly where would you place the paper to harness that energy? I'm going to let you ponder that focal point. Thanks for joining me on this explainer, and keep looking at the world through a curious lens.